Hello everyone. Uh, yeah, so let's get started with lecture 4. In the previous lecture, one of the key notions or one of the first notions that we have learned is notion of a group, and then we have seen the definition a couple of times while solving several exercises or going through several examples. So what you saw that yeah, the first condition is that the G has to be a set. The second condition is that we have to have a composition law, so which has to be a map from G cross G to G, and there is a certain property of that composition law that we expect that has to hold for any GHK inside G. And we also talked about the inverse, or for instance we tried to justify the usage of the article the while referring to identity element, right? So there is only one identity element, so this one is proposition 32, right? So the group contains exactly one identity element, so this justifies the usage of of the of the article the in the fourth condition of the definition of a group. Sorry. Yeah, and then we move on to the notion of inverse. So okay, so this is a notion that we did not introduce before proposition 34, okay, but from some of the prior examples that you have worked out, uh, it's we have worked out that indicates that, or that suggests that we may wish to call the elements x and y as inverses or the inverse of G. We can call x as the left inverse of G and y as the right inverse of G, and so on. But before getting into all that, if we go through proposition 34 and its proof, we see that under this kind of circumstances, I mean under such a circumstances, uh, I mean that, so if G is a given element and x and y are elements of G such that this condition holds, so then one can show that x is equal to y, and for any other choices of such elements x prime and y prime, one can indeed show that all these four elements are the same. So from now on, we decided that we'll talk about, we'll talk about that element, I mean call that call that element x or y, whichever, as the inverse of of a given element G, of the given element that you have started with. So we decided to denote it by G raised to minus 1. And yeah, we have set this convention, and I left this exercise for you. I hope you have done. This is elementary, although I expect you to kind of write down all the details, okay? I mean, this is easy, but I mean, this is usually recommended to do certain easy exercises too, along with some difficult ones. Yeah, and then we moved on to the notion of abelian group, and I hope you have worked on these exercises. So this is question 38 and exercise 39. Okay. Yeah, so now let's try to do something elementary which we are familiar with for several years. So here is a problem. So it says that if x and y are real numbers such that 5 plus x is equal to 5 plus y, then you have to show that x is equal to y. Yeah, this is quite easy. So because you can just cancel 5 and 5 from both sides. So that's what you have done here. And then you immediately get x equal to y, right? So you get it by cancelling 5, right? Okay, so what do you mean by cancelling? So cancelling could mean actually striking off, right? You're just striking 5 off from both the sides, right? That's what you're doing. So cancelling means striking off, yeah. But so what is the justification for, I mean, such a striking off to be valid? Okay, so we can strike, I mean, you can just remove 5 from both sides. Then what is the guarantee that then what will be left with, namely x and y, they have to be equal? Okay, so the idea is the following. I mean, if we try to write down the details, okay, so this is something that I think we have seen in some form or the other while learning addition in high school algebra. Okay, I think this was stated somewhere in the book, but maybe we didn't focus. I don't remember if I focused when I first learned algebra in school. So let's try to go through that, okay? So what we do is that we add minus 5 to this quantity 5 plus x, okay? And since 5 plus x is equal to 5 plus y, So when minus 5 is added to 5 plus x and it is also added to 5 plus y, they would provide two equal numbers, okay, that process. And now we use the associativity of the addition law of real numbers, so that allows us to combine minus 5 and 5 together on the left hand side and also on the right hand side, and that yields 0 by definition of minus 5, right? And since 0 is the identity or additive identity, okay, we get that x is equal to y. So here you may see that we are saying the element 0 is the identity of the group of real numbers. So you can ask, what is the composition law? Yeah, I mean, this is a standard practice to not state the composition law when there is no room for confusion. So throughout this course you will see certain groups coming into the discussion over and over again. So one of these groups is the group of all real numbers, okay. And then if you deal with such if you deal with such real numbers, then it is understood that here, I mean, the composition law that we have in mind is the addition, okay. Or if you deal with the, I mean, if you say that, look at the group of non-zero real numbers, it is implicit that we have the multiplication as the composition law, okay, in mind. Okay, anyway, so what we are just trying to justify this high school style of solving such problem by striking of 5, okay. We just try to go to the justification of this process, this cancelling 5, okay. So this is something that holds not only in the group of all real numbers, but in fact in any group. It doesn't matter whether the group is finite or infinite. So I have already started writing that let G be a group, okay. So yeah, so you may say that, I mean, how can G be a group? It should be this should be G comma star, right? Yeah, I agree. I mean, this has to be G comma star for sure, but I mean, this is standard practice to not indicate the composition law, okay. For instance, even if I write star, you wouldn't know how does, I mean, you wouldn't know a star explicitly, right? We know that star is a function from G cross G to G, right? Anyway, yeah, so from now on, very frequently, or maybe almost all the time, we'll drop this composition law, okay. And so in that case, to write G star H, I mean, so we'll write G star H just as G times H. We'll just put these elements next to each other, okay, to denote G star H. Okay, so suppose x, y, z are elements of G such that x, y equal to x, z, and as you can see, you can cancel x from both sides, okay. So this proposition says that if we have three elements x, y, z inside a group G such that x, y is x, z, then we will have y equal to z, okay. And also similarly, if you have this equality that y times x is equal to z times x, then you would have y equal to z, okay. Yeah, so you need to do the proof, and the proof is no different from what we have just seen in the context of real numbers. So suppose we assume that we are given with three elements x, y, z, such that x, y equal to x, z, then you multiply these quantities by x inverse from the left, so we obtain this, and then you use associativity to combine x inverse and x together on both sides, so that leaves us with the identity element times y and identity element times z, right? And by property of the identity element, we know that it immediately follows y equal to z. And similarly, if we assume yx equal to zx, then you can put, I mean, you can multiply these two quantities by x inverse from the right, and then use associativity of the composition law to combine these two elements together, okay, x and x inverse. Then you would get y times identity z times identity by using property, by the defining property of the identity element of G, it follows that y equal to z. So yeah, so this sort of, I mean, removing x from both sides, the strategy or that usual striking of policy, it works, but I mean, thanks to this justification, okay. So this is needed, this is crucial, okay. Yeah, so yeah, so whenever you're using, I mean, such striking of thing, so please refer to the cancellation law, okay. So mention that, please mention that by cancellation law from this equality, it follows y equal to z, okay. This is good for your practice, at least for next couple of weeks. Okay, so here is a notion that we are going to learn. I don't know if this is a good idea to first start with an example or first start with the definition. Maybe let me get into an example. Just give me a moment. Yeah, so here is an example. So it focuses on this set, right? This set you have seen in one of the exercises, probably in lecture 1 or in 2, I suppose. Okay. So if you look at this set, then this forms a group. Okay. This forms a group under the composition law. This, okay. So which is coordinate wise multiplications. You multiply A times C and you multiply B times. You multiply A and C and then you multiply B and D, and what you get is the composition of these two elements of this set. Okay. So one can show that this does form a group under the composition law. So that is an example, and this is an exercise for you. It says that prove. So this is an exercise for you to show that the set forms a group under this composition law. Okay. Yeah, and then note that you could do something like the following. So you can consider a subset, for example, maybe this one. This looks nice. So if you look at this subset, this is a subset of the set that you have started with. Okay, so this is a subset of this set, and note that this one, for instance, contains the identity element of this set, right? Okay, one can show that the identity element of this group is equal to this element 1 comma 1. Okay, so yeah, so here you note that this also forms a group under the same composition law. Okay, so and this is a subset of this. Okay, so somehow you can think of this is a substructure of this structure. By structure I mean a set accompanying, equipped with its group law or its group structure. Okay, so this one is a subset of this, and composition law, they are defined by the same formula if you want. Okay, yeah, one has to be precise. Just give me a moment, I will be so. So one can one can consider these two sets. On the bigger set we define the composition law using this formula, and on the smaller set also we use the same formula to define composition law, and then you will see that this also forms a group, right? So this somehow leads us to the notion of a substructure within the structure of a group. So such substructures are called subgroups. Okay, so if you start with a group G, okay, then a subset H of G is called a subgroup if all these conditions hold. So for instance, so let me go through that. So it says that whenever we pick two elements from H, their composition. So if you want, then this is A star B, where star is the composition law of G. I'm just writing this just to make sure that you don't have much difficulty, but please try to get used to this kind of notational convention. Okay, this is standard. Okay, standard to drop that composition law and just write AB, which stands for A star B, where star is the composition law of G. Okay, it could also be, it could have also been G comma circle. Then of course AB denotes A circle B, etc. Okay, great. Yeah, so the first condition is that the product of any two elements of H, this kind of expressions are called product for obvious reasons, because we use the letter AB to we used to use the letter AB to denote product in our school days. So yeah, so the product of any two elements of H is an element inside H. It has to lie inside H, and H contains the identity element of G. Okay, and whenever we pick an element, its inverse has to lie within H. So you can ask me what is A inverse. So A inverse, the inverse of A inside the group G. Okay, the element A inverse, so which denotes the inverse of A in the group G. Okay. Yeah, so yeah, but while discussing this exercise, I was saying that this forms a subgroup, or this forms a group in its own right? So if you define if we somehow how to call it, restrict this composition law to this subset, then this defines a well-defined restriction composition law on this set, on the smaller subset. And yeah, associativity will automatically hold, because associativity holds in the bigger how to call it, inside the bigger world, inside the bigger group. And one can show that this, the fourth and fifth condition is also valid within this subset, combined with the composition law, the restricted composition law. So the upshot is that this is a group in its own right, right? Although and I mean, I use that this example to motivate the notion of a subgroup, right? But here, I mean, we do not even kind of saying that H has to form a group, right? I mean, again, if you observe these conditions carefully, then you will see that we have done at least some of the necessary how to call it, necessary steps or necessary information that you need to show or claim that H has to be a subgroup. That is already there. For instance, if you pick two elements A and B, and then I mean, you just combine A and B using the composition law that we already had within our group G, then the element that we'll get, that lies inside H. Okay, and also we have this notion of inverse. You'll see just in a moment that these three conditions actually say that H is a subgroup of G in an appropriate sense. Okay, let me try to explain. So suppose H is a subgroup of G. In other words, H is a subset of G satisfying all these three conditions. And then you see that then if you what you had done earlier, we said that within this subset, if we define the composition law using the same formula, in other words, you are restricting the composition law of the bigger group to a smaller subset. Okay. So if you try to do that, so if you start with a group G comma star and use the composition law of the group G to define a composition law on a subgroup H, note that this is a subgroup. Okay, I mean, by hypothesis. So if you define if you use the composition law of G to define a composition law on H, okay, so if you pick any two elements H1 and H2, we compose them within H as per this new composition law, which is the restriction of the, or rather, I mean, which is called the induced law. I mean, so I mean, if you want, this is the restriction of the composition law of G, and the standard terminology in this case is that we induce this composition law on H from the composition law on G. So this is called the induced law of composition or induced composition law. Okay, the claim is that, or the elementary observation is that, H forms a group under this composition law. Okay, so H forms a group under the composition law on H, that is obtained by restricting the composition law of star to H. Okay. Okay, great. So now the task is to establish this claim. Okay, and this is an exercise for you to show that this claim is correct, that the statement is valid. Okay, as usual, the first task is that this does define a composition law in H. In other words, we need to first make sure that the image of the map star is contained inside H. Okay, so I hope you immediately see, or at least if you again go through the definition, you will see it immediately, because we are saying that A times B, which is A star B by definition, we are saying that for any AB inside H, A star B lies inside H. So that already says that whatever H1 and H2 you may have in mind from H, if we compose them using this composition law, which is by definition H1 star H2, so that has to lie inside H. Okay, so by the first condition, we are done with the first part, right? Now it remains to determine whether H forms a group under this induced composition law or not. In other words, whether this remark or this claim is true or not. Okay, one can show that this is true, as I have been claiming since then, and also it is stated here, written. Yeah, so for the third condition in the notion of a group, so you need to verify the associativity. So associativity is a property of this composition law star, so it has to hold for for its restriction to, or for the induced law of composition. Okay, so because you would like to show that H1, now how to write this star? Okay, just let me try. So H1 Sorry, I would not be able to write this star, or maybe this looks good. So you have to show that h1 star h2 star h3 is same as h1 star h2 star h3, right? That is what we need to show. But the left hand side is equal to h1 circle, not circle, star. So it's h1 star h2. I'm sorry for this bad handwriting. So this one and this stars are this star, okay? I mean this star, and this star is this one. So probably this is called asterisk. Okay, I don't know. Anyway, so this is so you have h1 star, then h2 star h3. So we know that so this is what we need to show. Okay, again for all h1 h3 inside h, right? This is what we need to show. So need to show, and so this is what we know. This is what we know, and so we also have this by associativity of the composition law of G, right? Yes, so we know, I mean, we have this equality, we have this equality, and we know that these two quantities are the same, right? So since these two are the same, these two have to be same. So this equality follows, okay? So this one follows from, okay, from all this, maybe I should have put this in the same color. Oops. Okay, then using all these violet implications, so this follows. I'm sorry for this unorganized stuff. This is just to provide you some hints for this, or kind of certain ideas, although which is quite elementary, but I think you should be able to do. But I thought of writing all that just to give you an idea. So anyway, so this is an exercise for you. Please complete this exercise 2. Part 1 is already discussed. Please try to even go back to, I mean, try to do it on your own. This is elementary, but please try to redo it, okay? Fine. Then, yeah. Okay, so then here are certain exercises that we would like to focus upon. So we have seen this group mu n, okay? Recall that this denotes the group of nth roots of unity. So this is the solution of the equation z power n equal to 1 in C, and this is equated with multiplication, okay? Multiplication of complex numbers, and that forms a group of size n, because this has got exactly n solutions. Z power n equal to 1. This has got exactly n solutions inside C. So one can consider this group. So mu6, for instance. So this will have 1, and then it is what it is. So probably this is at an angle of 60 degree, etc. Okay, so you know that the solutions are e power 2 pi I over n, and then k. Okay, so k runs over all the integers, or maybe the integers between 1 up to n, etc. So one can, if you draw mu18, try to locate the points inside the complex plane, you will immediately observe that mu6 is contained inside mu8. Or you can also see that if you have a complex number, you can also see that if you have z satisfying z power 6 equal to 1, then this is automatic that z power 18 is also equal to 1. Okay, so any solution of this equation is also a solution of this equation. It follows that mu6 is contained inside mu8. Okay, yeah, I mean, it is not a bad idea to use the picture, but again, you would like to do things in general, as you see from this exercise. So we start with two positive integers such that m divides n, then mu m is contained inside mu n. Not only that, we need to show that mu m is a subgroup of mu m. Okay, that might be a confusion. Let me just highlight that mu m is a subgroup of mu n. Okay, yeah, so note that at least this statement is unambiguous, because mu n is already a group, and this is already a subset. So you can try to see whether that subset forms a subgroup of this group. Okay, and this exercise says that we have to show this, so you know that it is, assuming that this exercise is correct, and then we have to just prove it, right? The first thing, I mean, is good to note that mu m is indeed a subset of mu n, okay, which is not true in general. For example, mu2 is not contained inside mu3, okay. So here we do have that mu m is contained inside mu n thanks to this hypothesis that m divides n, okay. And now if you just go back to the definition of a subgroup, then from the first condition you need to show that if you pick any two elements from H, their product has to lie inside H. H has to contain the identity element, which is usually quite easy to verify, I mean, at least in this example. And then the fact that this element A inverse lies inside H for any A inside H. So to verify the first condition, we just observe this, recall this fact that the product of any two mth roots of unity is, okay, this should be an mth root of unity, is an mth root of unity. The product of any two mth roots of unity is an mth root of unity. So the first condition is verified. For the second condition, you need to show that H contains the identity element of G. So the first task is to determine the identity element of G, right? So since we have already solved this exercise that mu n is a group, we know that what is the identity element of mu n. We know that that is 1, okay? So you know that the identity element of mu n is 1, and we also know that 1 is an element of mu m, that is 1 power m equal to 1, right? Since 1 power m is 1, so 1 lies inside mu m. So it follows that the identity element of mu n is an element of mu m. It is contained inside mu m, okay? Great. And now the third condition, which says that for any A inside H, the element A inverse lies inside H. So, I mean, that is something that you already know, because if you pick an element from mu m, this is an mth root of unity, okay? So if you look at its reciprocal, so since z, if you pick an element z inside mu m, so z power, we know that z power m equal to 1, right? So it also follows that, I mean, z power, how to call, I mean, if you pick an element z from mu m, then it's inverse, then it's inverse inside the group mu n, that has to be an mth root of unity, right? Because if z power m is 1, then it follows that 1 over z that raised to m is also equal to 1, right? So it has to be an element of mu m, I mean, then it follows that mu m is a subgroup of mu n under the situation that m and n are positive integers with m dividing n, okay? Yeah, I mean, so as you see that the group mu n is coming over and over again, and also there are certain exercises, at least I mean, maybe not quite a lot, but few exercises that I have suggested in the that I have provided in the lecture notes, or just asked to work on during the lecture, I mean this recorded lecture. So I mean, this was one of the exercises to show that mu n is a group under multiplication, okay? This gives an interesting family of groups. So you know that mu n contains exactly n elements. So for each positive integer n, you know that there is a group containing exactly n elements. So if you have 5, then you look at mu 5. If you have 100, you look at mu 100, and so on, okay? And if you have n, you just look at mu n, okay? Yeah. So let's try to go through some exercise. So it says that if you pick a group and denote its identity element by E, then you have to show that G is a subgroup of itself. I leave it to you to decide. And now there is a to show, and now I leave it to you to decide whether it is true that the subset of G consisting of the single element, namely the identity element, that whether this is a subgroup of G or not, okay? So this is what we need to figure out. So please try to work it out. Okay, so while studying sets, we have seen the obvious fact that subset of a subset is a subset. By that I mean, if you have a subset X, how to write maybe, so if you have a subset, I mean Y of Z, and if you have a subset X of Z, then it follows that X is a subset of Z, right? So that is what we are trying to show in the context of, I mean, so here this is the substructure for the for sets, if you look at subsets. But while studying groups, we are not interested in any we are not interested in any subset of G. We are interested in the subsets of G satisfying these properties. Okay, so if you are just interested in such subsets, in other words, if you are interested in subgroup, then an analog of this implication holds. Okay, uh, yeah, I just thought of making one remark. I mean, just a remark about some notation. So as you see here, I use this arrow. I mean, not even the arrow is correctly drawn, but such arrows are, I mean, such arrows are undoubtedly meant for usage in the blackboard. This is not a mathematical notation. So if you want, you can, oops, if you want, you can strike it off and replace it by the correct one. Okay. Maybe I'd like to put it in this form. Maybe just let me erase. This will remain with you because, I mean, you're already watching it. Yeah, that x is a subset of y and y is a subset of z. That implies that x is a subset of z. Okay, I'm sorry, I just somehow try to write things down in the blackboard style where one can use certain understood notations, something like this, but this is not allowed in mathematical writing, not at all allowed. I mean, you can try to find one textbook, a reasonably, I mean, a reasonably recent and a modern textbook, you will not find the usage of such weird arrows. Okay, this is not allowed. Okay, and anyway, so this exercise says that if you have a subgroup H of a group G, okay, then by the previous, okay, this exercise which actually asks you to determine, but you know that by this remark that H is a group, okay, under the restricted or induced composition law. So we can still, since H forms a group under the induced composition law, we can talk about subgroups of H. Okay, that certainly makes sense. That's the first thing to note. Yeah, and now just note that this exercise says that if you have a subgroup of G, H, and if you have a subgroup of H denoted by K, then you have to show that K is a subgroup of G. Okay, the first thing is to note that K is a subset of G. That is for sure, because K being a subgroup of H, it has to be a subset of H. On the other hand, since H is a subgroup of G, it has to be a subset of G. So K is a subset of H and H is a subset of G. So it follows that K is a subset of G. So we have to show that this subset K of G actually forms a subgroup of G. Okay, so please try to work it out. Great. Now let me have one interesting example. Okay, so we pick an integer n. It could very well be 0. So nothing to worry. It could very well be 1 or minus 1, 2 minus 2 and so on. So we denote the set of multiples of n by the symbol nz. So nz stands for all the multiples of n, all the integer multiples of n, that is n times k, as k runs inside z. So the set of all, if you want, integer multiples of n. Yes, so nz consists of all the integer multiples of n. You have to show that nz is a subgroup of z. Okay, again, the first thing, this is a good thing to check, or I mean, for ourselves, because we may fall, I mean, we might be just too ambitious and we may end up having an incorrect statement. Okay, so just first observe that nz is indeed a subset of z, because product of any two integers is an integer, so it follows that nz is a subset of z. Okay, so now I mean, you have to first, I mean, there are three conditions to check, 1, 2 and 3. The first condition says that if you pick two elements from H, so which is nz, their product has to lie inside H, right? So if you pick A and B from H, you know that AB has to lie inside H. So AB stands for A star B, where star is the composition law of the bigger group. So what is the composition law of the bigger group? So we should be careful. The composition law is the addition. Okay, so addition is the composition law of this group Z. Okay, so you have to show that A plus B lies inside NZ for any AB inside NZ. Okay, so this stands for AB here. So recall that we decided to write AB for A star B, and star happens to be plus here, the addition. So that's why AB, the apparent product, has been replaced by the sum. So there is no room for confusion after you have observed that this AB, which is not A times B, but this is A composed with B as per the composition law, so which is plus, so that's why you have to write A plus B, okay? So if you have observed this, then there is no room of confusion. There is no room for any confusion. Okay, so since the sum of two multiples of n is a multiple of n, this is easy to observe. Nk plus nk prime is n times k plus k prime. So it follows that the sum, or if you want the composition here, but since here the composition law has got a nice name, namely sum, so we prefer to use that terminology sum here. So since the sum of any two elements of nz, since the sum of two multiples of n is a multiple of n, it follows that the sum of any two elements of nz is an element of nz, right? Okay, and of course 0 is the identity element of z, and of course 0 is an element inside nz, because you can take k to be 0 to get 0 as a multiple of n, right? And then you have to pick an element a of nz, and then you have to look at its inverse, which is the integer minus a, and this is certainly a multiple of n, right? Because if a is equal to nk, then minus a is n times minus k, right? And hence it has to lie inside nz. So you're done with this example, right? Okay, so now here's an exercise for you. Show that subgroup of an abelian group is also abelian. Okay. Show that subgroup of an abelian group is also abelian. Here is an exercise for you, maybe exercise 51, but in that case, this 51 will be in trouble. Anyway, so here is an exercise. Determine whether a subgroup of whether the subgroup of non-abelian group is non-abelian by necessarily non-abelian. Okay, is necessarily non-abelian. Okay, so please try to work on this exercise. Yeah, and then we have this nice theorem. So it says that which is an analog. Sorry. This is this is not an analog of anything. I had something else in mind, which is just in the next page. So somehow after scrolling, I just got a bit confused with that. So here is a theorem that that is very useful, because it allows us to okay, so this is about subgroups of a group G. So if you are given a subset of H, if you are given a subset H of a group G, then this theorem allows us to have an alternate method to verify whether that subset could form a subgroup or not. Okay, by that I mean we do not need to work out all these three we do not need to verify all these three steps one by one. Okay, so it's just kind of a one step quote unquote how to say, there is a one step criterion and that determines whether a subset forms a group or can form a subgroup or not. More precisely, if you have a non-empty subset, okay, so it doesn't apply to empty subset. Okay, so you cannot apply this theorem to empty subset to deduce that and the empty subset of a group G is a subgroup. You cannot. Okay, so it says that a non-empty subset H of G is a subgroup, undoubtedly subgroup of G, okay, if and only if AB inverse lies inside H for any AB inside H. So there is something that I need to explain. So this part. So what do you mean by if and only if? It should be that, and then even after rotating it doesn't help much. Okay, not to be bothered. Yeah, so this says that a non-empty subset H of a group G is a subgroup of G if and only if AB inverse lies inside H for any choice of AB inside H. So I do not know if you have met this phrase very frequently in your mathematical training so far. So let me try to explain. As you see, there are two, how do you call, like, okay, there are kind of two parts of it, if and only if. So with the if thing, we shouldn't have any difficulty because we are used to, I mean, we know this word for several years. So we say that, I mean, for example, if you have a statement A and if you have a statement B, so if you say that A holds if B holds. So for instance, A could be the statement x square equal to y square, and B could be the statement x equal to y, right? Then you know that this holds if this if this statement x equal to y holds, right? uh, just let me highlight. Yeah, sorry for this sudden pause. uh, yeah, so here as we see that, how do you call that, I mean, I just tried to explain you the statement using an explicit example, okay, which you will see immediately. So I mean, the aim was to kind of tell you this meaning of if, which you already know. So you're saying that, so we're saying that if x equal to y holds, then x square equal to y square has to hold. Okay. Sometimes we write in shorthand. We write that x equal to y, it implies x square equal to y square. Okay. So of course this statement means that, I mean, if this holds, so that is under this hypothesis we will have this, and this also says the same thing, that under this hypothesis or under this, how do you call, like, I mean, input or hypothesis, we will have this equality. So this is implication. Okay. So just let me try to sorry for the sudden pauses. Yeah, so okay, here is one remark for caution though. So here is one warning. So this should not be confused with if. Okay, I mean, although you may have the feeling that I'm using the symbol for if, but I'm not. Let me try to explain. I mean, this is quite easy to see because we are not saying that, maybe, oops, we are not saying x square equal to y square. If I now replace if by this, we are not saying that x square equal to y implies x square equal to y square implies x equal to y. Okay, so this is not I mean, this is not a shorthand for if. Okay, because I mean, we have just reversed the order. So we have put x equal to y first, and we have put this the conclusion x square equal to y square next to it. So anyways, you have understood the meaning of if. I mean, anyway, you have already been familiar. Oops, I try to rotate. Okay, so now let me try to explain what do you mean by only if, maybe on the same page. Just give me a moment. Yeah, I hope this is still good. Okay, so here is one example. So I could say that, I mean, okay, here is, I mean, rather here, let me try to explain. So I say A holds only if B holds. Okay, so an example is that, now how to give an explicit example of that? Okay, now let me think. Of course, I mean, there is one example right here. Oh, sorry. Here is an I mean, this example, I mean, this is a true example of I mean, this is a valid example of such a statement. But okay, so I'm not able to think of anything simple as an example. So let me try to explain what I'm trying to say. So Yeah, so we say A holds only if B holds. So this means that, so this, sorry for this bad handwriting. This, oops, this means that when, oops, sorry, when A holds, or, okay, when A holds, then B has to hold, or in other words, the validity of A, I mean here of course A, I mean, stands for a statement, okay, I mean not stands for, A denotes a statement. So the validity of A forces B to be true. So in other words, as you see, that would, I mean, if I mean, when the validity of A forces B to be true, that means if A is true, okay, then B has to be true. So that I mean that the same as saying A implies B in notation. So thus, if you say, yeah, if you say A holds if B holds, then you are saying, oh, maybe I should also, oops, just give me a moment. So that means if B holds, right? So B, so it means that B implies A, okay? So A holds if B holds, that means that B, I mean when B holds, so that's it, when B should imply A, okay? So A holds if B holds, the same as saying B implies A, and when you say A holds only if B holds, that means A implies B, okay? So now let me just try to summarize once again. A holds if B holds, that's the same as B implies A. Okay, so let me write it down. A holds if, just let me try to watch out. A holds if B holds, so that's same as saying, I mean, this is shorthand for, I mean, here, this is shorthand for what I just said, that A holds if B holds, and A holds only if B holds. That means that A implies B, okay? And yeah, and just one quick remark that B implies A, so sometimes we just put the picture in the other way. So if B, how do you call this, from active voice to passive voice, if B implies A, that means A is implied by B, right? So this is written in this way, that this stands, I mean this means that A is implied by B, okay? So all these three statements, they are the same, that A holds if B holds, and B implies A, and A is implied by B. And here also you can write one equivalent one. So here B is, oops, sorry, my iPad was just going to turn around. Anyway, so this means that B is implied by A. Okay, so now if you get to see, for example, A holds, okay, let me just remove that word holds, A if and only if B, okay, let me just put holds, okay? So the if part stands for A if B, right? So B should imply A, so that's what is being done. And this only if stands for A forces B to be true, so A implies B, okay? So if you want, oops, yeah, so oops, yeah, so if you want, if stands for, or this is a shorthand for if, and this is a shorthand for only if, okay? So here I'm saying that this is a shorthand for if. Earlier I used this, okay, so do not get confused. So I mean, this is not a shortened for if because I have reversed the statements, okay? I have reversed the statements. So x equal to y is placed here and x square equal to y square is placed here, okay? So this is not a shortened for if. The shortened for if is this, okay? This straight implication or this direct implication, okay, not this direct implication symbol, but this reverse implication symbol, okay? And only if denotes this direct implication symbol, okay? So please keep this in mind. There is not much to understand here, okay? Probably what one needs to understand is the English meaning of this word if and only if, right? And I mean, if you want to use mathematical symbols, I mean, you know, for this to kind of simplify this process of keeping the mathematical meaning in mind, you can assume that, or you can have that, you can keep it in mind that the shortened, I mean, if stands for this symbol, that means A is implied by B, and only if stand for this straight implication symbol, that means that A implies B. Okay, so now we're in a position to understand this statement and then establish it. So this says that a non-empty subset H of a group G is a subgroup if and only if for any AB inside H, AB inverse lies inside H. So let's try to go through the proof. So let's try to work out the if part, and this is a standard convention to write this, or maybe yeah. So this stands for the if part, right? So A if B, that means A is implied by B, okay? So if I initiate the proof using, maybe this looks a bit too ugly, let me rewrite. I mean, so ugly that this is incomprehensible. So if I begin a proof of such a statement, sorry, this is still looks quite terrible. If I begin a proof using such a notation, so that means when we are in an if and only if context, it means that we are proving A if B, okay? So you are assuming this, okay? You have to prove A if B, so you have to assume B, and then you have to establish A. So you assume that AB inverse lies inside H for any AB inside H. We need to show that H is a subgroup of H, okay? Yeah. So okay. So there are a few tasks to do. There is condition 1 and condition 2 and condition 3 to verify. So we'll first start with condition 2, okay? So we are allowed to do it here, okay? Do you know some instance where you are not allowed to somehow, we are not allowed to kind of jump onto the second or third or maybe fourth condition before verifying the first or second one? Sorry, I need to have a quick break because my laptop doesn't have any charge left. Just give me a moment. Yeah, so I'm back. So as I was saying, here we will first verify condition 2. I was asking you if you're aware of any such instance where you're not allowed to move on to maybe the second condition without verifying the first, or maybe we are not allowed to move on to a third condition without verifying the first two. So please think about it, okay? Yeah. Okay, so we are trying to establish this theorem, namely the if part of this. So first note that since E